So today I'm going to be talking to you about privacy in Bitcoin's peer-to-peer layer. And this was joint work with some talented collaborators, Shailesh Venkatakrishnan, Surya Bakshi, Brad Denby, Shruti Bhargava, Andrew Miller, and Pramod Vishwanath. Okay, so to start out, I'm going to give a very quick primer on what Bitcoin's peer-to-peer network is doing and what the privacy problem that we're worried about is. So most of you probably know, users in Bitcoin are connected over a peer-to-peer network of TCP links. So users in this network are identified by their IP address and their port number. So users also have a second identity, which is their address or public key, however you want to think about it. So when Alice creates a transaction and wants to send it to Bob, the first thing she does is to broadcast this transaction over the underlying network. Until all the nodes receive it, and now the miners can start racing to append this transaction to the public blockchain. So one of the key privacy requirements of this system is that Alice's address and her real identity should remain unlinked. Okay? And in particular, in this talk, I'm going to be concerned with linking Alice's Bitcoin address to her IP address. So this is not all the way towards completely de-anonymizing someone, but it's kind of an important step. If you have someone's IP address, you can sometimes narrow down who that person is. So my claim is that the way the current Bitcoin network works, it makes it easier, or relatively easy, to link someone's address to their IP address. So why does this happen? Well, today, messages on the P2P network spread according to a process called diffusion. Okay, so the idea here is that each node is going to take each transaction and spread it with independent exponential delays on each edge. So here lambda is the parameter of that exponential random variable. Okay, so if Alice spreads the message to this neighbor, the blue neighbor then relays that message with fresh independent exponential delays to each of its neighbors, and so forth. And so over time, this message spreads, this transaction spreads over the network. And the problem here is that if we have a set of corrupt nodes, so in this example, let's suppose that the red guys are spies that are trying to de-anonymize a user, they can use the timestamps that they see along with the structure of the graph to try to infer which node was the source of a particular transaction. Okay? And so if they can infer that source node, then they know the IP address, and they can make this linkage that we said was bad. Okay? So the problem here is that diffusion, this spreading process that we're using, is actually vulnerable to source detection. And this has been explored in a bunch of papers, including a few practical ones that were specifically tailored to Bitcoin's peer-to-peer network, and some recent work that I did with some collaborators. And the point is, without expending too many resources, you can make this linkage with probabilities that are exceeding like 50%, numbers that are kind of scary. So Dandelion was a project that we worked on, an attempt to build a lightweight transaction propagation algorithm with theoretical, provable anonymity guarantees. So today I'm going to be talking about what those guarantees are and trying to give you some intuition about why Dandelion works. So before I go into Dandelion, I want to answer some FAQs. So these are questions that we get all the time, which is why don't you just use existing solutions? So the first question we get most often is, why don't you use Tor? Okay, so the idea here is that if Alice, the red node, has a transaction, she'll send it through Tor to a randomly selected other node, the blue one, and the blue node will diffuse the message for her. Okay? And so because she's using Tor, the blue node doesn't know who Alice is, and so she gets privacy here. And in fact, this is addressing the same problem. And if you're worried about privacy, you can and should use Tor. But one of the issues here is that in order to adopt this solution, you have to be aware of the privacy vulnerabilities in Bitcoin. And a lot of users simply aren't. Or even if they are, they might not have the technical expertise to do this routing through Tor. So if we want Bitcoin to become kind of a mainstream payment system, it's important to build in mechanisms that protect privacy for all users, not just the ones that are maybe particularly concerned about privacy. The second solution that people discuss is kind of similar conceptually, which is why don't you build some kind of onion routing or something like onion routing into the network itself? So for example, Monero has been integrating I2P into their peer-to-peer network since I think 2011. And this also addresses the exact problem that we're trying to solve, but one of the problems with this seems to be that implementing this is actually really time intensive, requires a lot of developer hours and expertise. So despite working on this since, I believe, 2011, I don't think this integration is complete. Oh, 2014, sorry. Sorry?
It's not implemented yet, it's soon
to be implemented. I mean, my point being that it's even 2014, that puts us at like 4 years. So clearly it's a substantial implementation effort. And so it would be nice if we had something that was lightweight and kind of much easier to implement. So our goal with Dandelion was to propose a system that has theoretical privacy guarantees, is also benefiting everybody in the network, and is lightweight, easy to implement. So I'm going to start by presenting what our model was, like what are the assumptions that we made about our system, and then talk about the solution that we're proposing to optimize under that model. Okay, so I'll start with the adversarial model. So we're assuming here that we have some existing network in which a fraction p of the nodes are spies or are corrupt. Okay? So p, this is the only notation I'm going to ask you to keep track of. So this is the fraction of spies. The identities of these spies are unknown, and they observe all of the metadata that comes to them, including timestamps, other control packets, and so forth. These spies collude with one another, and they are, for the moment, let's assume that they're honest but curious, which means they follow protocol, but eventually I'm going to relax this assumption and deal with Byzantine nodes as well. Okay. So that's our adversary. Our metric for anonymity is based on the idea that in Bitcoin you have many users and each user can be generating multiple transactions. So to start out with, we're going to assume that we have n users, and each user is creating one transaction. So the adversaries goal, the goal of these spy nodes, is to create a mapping from transactions to users. Okay? And the level of de-anonymization that they achieve is a measure of how good is this mapping. Okay? So to measure the quality of the mapping, we use a metric that's commonly used in the machine learning literature, which is precision and recall. So in the context of this example, recall is measured as follows. We're going to look at our mapping, and we're going to count the number of correct arrows in this mapping. Okay, so in this case, we have one correct arrow mapping the red transaction to the red guy. But there are 3 total users, so we have a recall of 1/3. Okay. And I just want to note that in expectation, recall is identical to probability of detection. So this is a commonly studied metric in the anonymity literature. The second metric, precision, is kind of capturing some notion of plausible deniability. So precision is measured as follows. For each correct arrow in my mapping, I'm going to count how many other transactions were mapped to the same guy. Okay? So in this case, we have a correct arrow from red transaction to red guy, but 3 total transactions that are being all mapped to the same guy. So red guy gets a value of 1/3. And now we do the same exercise for all of the users, for blue guy and green guy. And so the average of all of those is going to be 1/3/3, 1/9. Okay? So this is recall and precision. And the goal of the adversary is to maximize their precision and recall. Okay? Whereas our goal is to design a distributed flooding protocol that minimizes the maximum precision and recall that can be achieved by any adversary, even computationally unbounded. Okay. So I took out most of the math from this presentation, but I have just one slide which is trying to give some intuition about how these metrics relate to one another. So if you glaze over during this slide, it's fine. I'll wake you up when it's over. Okay, so let's suppose that we fix a spreading protocol, like say diffusion, for example, and we fix an estimator that the adversary is using to link transactions to users. So that coupling of a spreading protocol and an estimator can be mapped to one point on this plane. It has some expected precision and recall. And the first thing we show is that that point has to lie between the blue and the red lines, like in that central kind of almond shape. And the reason for that is because we've coupled here our precision and recall by assuming that each user has one transaction. Okay, so this is kind of unusual for precision and recall curves, but that's the reason for it, and we'll relax that later. All right, now let's suppose that we cycle over every possible estimator that the adversary can use. Each one of those estimators is going to be associated with some point in this plane. And we're going to call the union of all of those estimators an achievable region. So this purple outline is an achievable region for a particular spreading protocol. So the next results we show are that no matter what spreading protocol you use, your purple region is always going to be to the right of the vertical dotted line. So you have a maximum recall of at least p. And above the horizontal dotted line. So you have a maximum precision of at least p squared, okay, where p here is the fraction of spies in our network. So what this means is that no matter what spreading protocol we use, the best we can hope for is that little green triangle at the bottom. Okay? So if you don't take anything else away from this slide, just remember we're trying to match the green triangle, and we'll come back to that at the end. Okay, so how do we improve the anonymity properties of the peer-to-peer network? Well, there's two basic properties that we want here. The first one is asymmetry. So remember in diffusion, you're spreading the message symmetrically, meaning I'm sending it at the same rate to all of my neighbors on the peer-to-peer graph. And this is bad because this means if I have spies in different directions, they're all collecting independent information about me. So we're going to try to break that symmetry by spreading faster in some directions on the graph and slower in others. And the second thing I want here is mixing. And here I don't mean mixing in the Chaumian sense. I mean, let's suppose that we have a sequence of 4 nodes with a spy at the end, and they're all passing their messages to the right. This spy is going to get 4 different transactions. And because they're all coming in on the same edge, the spy has no real way to say, transaction 2 belongs to node 2. It's not getting any fresh information about different transactions that would allow it to differentiate them. Okay? So these are the 2 properties we want. And what are the things we can actually control here? And there's 3 things we can control. The first one is the spreading protocol. So given a graph, given a peer-to-peer graph topology, what is the spreading method? So right now, Bitcoin is using diffusion. The second property is the topology. So what does the underlying graph topology look like? So right now, Bitcoin is using a random, approximately regular construction, but in principle, we could change that. And the third is dynamicity. So how often does the graph change? So right now, the peer-to-peer graph is changing on a slower time scale than what it takes for a single transaction to propagate. Okay? So we're going to propose Dandelion, which changes all 3 of these knobs. So the first aspect that we change is the spreading protocol. And the spreading protocol here is pretty simple. It has 2 phases. The first is the anonymity phase, or the stem phase, and the second is the spreading phase, or the fluff phase. Okay? So let's suppose the source node is this far left node. Okay? The source is going to pick exactly one of its neighbors and pass the message to that neighbor. Now the neighbor is going to flip a coin. If it lands heads, he'll pass it to exactly one of his neighbors. And this continues until somebody flips tails. So let's say the guy in the middle flips tails. Now we transition into the fluff phase, where the message just gets broadcast or diffused over the rest of the network. Okay? So the reason we call this dandelion is because the spreading pattern looks like a dandelion seed head. Okay, so why use dandelion spreading? What's good about this? Well, it turns out that dandelion spreading has an optimally low maximum recall. So remember I said the recall always has to be at least p, and dandelion achieves a maximum recall of p plus some smaller order terms, where n here is the number of nodes. So it's nice because it's optimal in terms of recall, and this means now instead of optimizing 2 metrics, precision and recall, we just need to optimize 1, precision. So that makes the optimization problem easier and more well-defined. Okay, so there's two other knobs that I said we were going to toggle. The first one is the graph topology. And so we're here actually going to use a line graph, right? So in this picture, let's suppose the blue lines are the regular peer-to-peer graph, the one that's in place today. So we're going to add an overlay graph called the Anonymity Graph, which is this black cycle graph. So now when a transaction comes in, it's going to propagate clockwise over the anonymity graph until somebody flips tails, and then they start broadcasting over the regular graph. Similarly, if a second transaction comes in, it also propagates clockwise over the same cycle until somebody flips tails. And it's important here to notice that all the transactions are propagating over the same line graph. Okay, so they're not all taking independent routes over this graph. Okay, and the third thing we change is that the dynamicity is high, so we're going to change the structure of this cycle graph frequently. Okay? So just to summarize, Dandelion has three components. It uses Dandelion Spreading as the spreading protocol. It has a line graph topology, and it changes the anonymity graph frequently. Okay, so under these assumptions, it turns out that Dandelion has a nearly optimal maximum precision, which is a logarithmic factor away from the lower bound that I told you earlier. Okay, so that's a small factor. And so theoretically, this is giving us some nice properties. Okay? And if we go back to that picture that I showed you earlier, here's our green triangle. So Dandelion is achieving a region that is pretty close to the green region. And if you compare this, especially with diffusion, which is what's done today, we're getting a pretty substantial improvement in privacy guarantees. Okay, so just to give you some intuition about why this is the right thing to do, I want to tell you about two types of graphs that don't work well. So the first one is a tree. So here, let's suppose our anonymity graph was tree structured, and everyone's passing their transactions up to the root of the tree. Okay? So this turns out to be bad. It has a precision of p, which is larger than p squared. So remember, p is a fraction, smaller than 1. And the reason for that is because of the SPI nodes in the second to the bottom layer. Okay? So for each SPI node in the second to the bottom layer, that SPI is able to automatically de-anonymize 2 nodes with perfect precision and recall. Okay? And in a tree, or in a regular tree, you have a linear number of nodes in this second to the last layer. So they're actually getting really high precision and recall because there are too many leaves in tree graphs. So we want a topology that doesn't have too many leaves. A second type of graph that we thought would work really well is a complete graph. So everyone's connected to everyone. And this is implicitly what's happening in systems like Tor and crowds. And this turns out to also be suboptimal. And the reasoning here is a little bit subtle. So to get good anonymity, you want different transactions to be progressing over the same route in the graph. Now, what happens in a complete graph is that you have so many edges that the probability of 2 transactions traversing the same path is actually really low. Okay, so the takeaway message here is that we want a topology that doesn't have too many internal paths. Okay, so a cycle graph is nice because we have no leaves, and there's really only one path that transactions can traverse over. Okay, so some of you might be thinking, well, how are we going to construct a perfect cycle graph? That's totally unrealistic, which is true. So what we propose to actually do in practice looks like this. Each node, let's suppose we focus on this highlighted node, is going to look at their outbound edges in the peer-to-peer network. Okay, so the edges that they initiated. Now, from those edges, they're going to pick exactly one edge to be their dandelion relay. Okay, so let's say the one that shook is our dandelion relay. Now, if a transaction comes, either from someone else or their own transaction, they're going to relay it over that dandelion edge. And the recipient is going to choose one of their outbound edges to be a dandelion edge and forward the transaction over that edge, and so forth until somebody flips tails. So what we end up getting is that each node is picking one outbound edge, and so we end up with an anonymity graph that's not exactly a perfect cycle, but it looks kind of similar, and it ends up having equivalent anonymity properties. Okay? Okay, so there's a number of, all right, so this was our initial kind of proposal, This was our initial proposal for Dandelion, and we've spent the last year or so trying to strengthen Dandelion against more realistic adversarial models. So what happens if you have Byzantine nodes that are disobeying protocol in kind of arbitrary ways? So in our recent publication, we talk about a number of these issues and trying to make the system more robust to these kinds of attacks. So some of these attacks include adversaries that can learn the graph very precisely, or adversaries that are looking at many transactions. So here we've assumed that each user generates one transaction, but if I'm generating like 100, and all of them are taking independent paths, then things could become problematic. So we deal with all of these issues, and because of time constraints, I'm not going to go into these solutions, but if you're interested, I would be happy to talk offline. I just want to summarize, one of the main takeaways from this exploration was that perhaps instead of using a line graph, which is like a 2 regular graph, we might use a 4 regular graph. So each node picks two outbound edges instead of 1. Okay. We also implemented Dandelion and ran some tests on the mainnet. So here we had 30 Dandelion nodes that were running in geographically diverse locations. And what we were trying to do here is evaluate the main trade-off, which is latency. Okay, so clearly by sending transactions along this path, you're delaying the time it takes for everybody else to get the transaction. So here I'm showing you the time for a transaction to reach 10% of the network on the vertical axis, and the path length of our stem on the horizontal axis. Okay, and so, as you might expect, this time is increasing as our path length increases. From 6 seconds when you don't have Dandelion running to about 8 seconds when you do have Dandelion running on average. So this kind of 2-second overhead in latency might be a problem in very high latency cryptocurrencies, but for something like Bitcoin where confirmation times are much longer than that, we think this could be a reasonable trade-off. So with that, I will leave you with a few take-home messages. The first one is that Bitcoin's peer-to-peer network has weak anonymity properties at the moment. The second one is that Dandelion may be a lightweight solution against large-scale de-anonymization attacks. And I want to highlight here that this is not a replacement for Tor. If you are an individual that is worried about your privacy, you should still continue to use Tor. This is more of like a large-scale privacy vaccination. And the third one is that we have a draft BIP, which we would very much welcome feedback on, along with a reference implementation. So with that, thank you all for your attention, and I'll take any questions.
Yes, so when you talk about flipping a coin, are you talking about 0.5 probability, or it's a parameter that you can choose?
Good question. It's actually a parameter. And so in our implementation, we choose the parameter to be about 0.1. So on average, your stem length will be about 10 hops.
Okay, and to continue on that, how do you make sure people enforce that? You have no way to verify it. So how do you know that the path you're taking is not already compromised, and then you keep feeding it with your information?
So what's nice about this is that you're effectively, like, the location of the transaction is a Markov chain. And so once you reach a compromised node, anything that happens after that is anyway not helping your privacy. So that's kind of accounted for in the bookkeeping, in the analysis, the fact that you might run into a malicious node in your stem.
Thanks for the talk. How do you, or what plans do you have to deploy that with backwards compatibility and stuff like that?
Good question. So the question was about backwards compatibility. So actually you don't, so we did some analysis on trying to understand what happens if you deploy Dandelion partially. So only like a subset of nodes are running Dandelion and everyone else is not. And it turns out even if you're the only one running Dandelion, you get some small privacy benefit. And as the degree of adoption increases, that benefit grows to the guarantees that I mentioned. And in terms of backwards compatibility, it's the way we've implemented it. If you are connected to someone that does not yet support Dandelion, you basically just start the fluff phase prematurely. So it means that you have a shorter stem, but there are no compatibility issues. So like when we were running our experiments on the mainnet, there were no problems. So.
How do you deal with Sybils?
So Sybils are kind of captured in this parameter P. So if you have a huge number of, so if like an adversary were to flood the network with Sybil nodes, that would just mean that you have a higher P fraction. That would be, so I think that's certainly a problem. One way to think about it, though, is to compare what would happen in the current networking stack versus if you were implementing Dandelion. So in the current networking stack, you basically end up with a probability of detection of 1 if you have a lot of malicious nodes in the network. Whereas our guarantees push that down a little bit. But at some level, if you have too many malicious nodes in the network that are trying to de-anonymize you, there's really not much you can do. So.
Thank you very much. I was wondering if you had any thoughts on the scalability properties of Dandelion on other cryptos like Grind for signature aggregation, and if this is something that you think could be one day done in Bitcoin.
What was the last part?
Is this something that could be one day done in Bitcoin? Aggregating signatures during the anonymous transmission phase.
Okay. So actually, this is something. I know there's a few people, or at least one person in the audience who was working on that. I'm not sure what they ended up doing with that aggregation aspect, and it's not something I've thought carefully about. But maybe, can I get back to you?
Yeah.
Sure. Thanks.
I have seen the presentation of, I think, the 0.15 version of Bitcoin Core, and it was said that Dandelion was already implemented or something like that, but probably I misunderstood. So it's not yet implemented in Bitcoin Core, right?
No,
no,
just, I don't think so.
And you're just developing a BIP or something like that?
Yeah, so we have a draft BIP online, and we have an implementation for people to look at, but we would love to have feedback from the community on ways to make this more palatable, or if some version of this could be eventually make it into core.
Thank you.
This may be going too far ahead, but what do you think the implications would be of implementing Dandelion for layer 2?
Could you be more specific? I'm not sure
what
you have in mind.
I don't know. What do you think? Just the consequences of implementing Dandelion in addition to Tor, what that would do to Lightning or security vulnerabilities within Lightning using Dandelion on the mainnet.
So Dandelion has a lot of similarities with things like onion routing, which are currently used for privacy in the Lightning Network. So in principle, you could use some of these same ideas of like choosing your onion route in a way that is consistent with these kinds of privacy guarantees. I think the latency trade-offs may become more substantial there, depending on why people are using it. So if they're using like Lightning Network because they want very low latency, they might not be willing to tolerate these additional latency measures. But purely from a privacy standpoint, I think some of the ideas could be integrated there.